welcome back to the open class and the first open class of the year. So I am Desire, and today I will be taking you through part of what we started the year that has passed us with regards to using the box warehouse and the simulation that's provided by us to learn things about robotics and to also understand some basic things that you can do with that package that's being offered. So what we're gonna do is I'm gonna switch to my computer screen real quick, and then we will start walking through what we're going to be doing today. And we have a lot to cover, and we're also going to create some kind of cliffhanger so that we can have you guys come back again and want to learn more on top of the things that we were going to talk about in this open class. So let me just switch to my screen right now, and I'm hoping you can see my screen. So let me see if I can see the messages. Just one sec. All right. All right. Just give me one more sec. All right. So what we want to do today is to understand things about executors in ROS 2 and why we need them and how they join with the things that we spoke about in the previous classes, which is basically doing some form of obstacle avoidance by being able to receive LiDAR scan data that's coming from our robot. So what I'm going to do is I'm just going to open the simulation real quick so that you can see what the simulation will look like once yours is loaded. And if you click on it and you use your mouse, you just drag down while having the right button pressed down, you should be able to see this planar view of the robot. So we will be working with this red one. So if you can zoom in, you will see this red one here, the fastbot 1. So this one is called fastbot 2, this one is called fastbot 3. So this whole setup, that what we call the box warehouse, you can see here box warehouse, is something that is not just offered in simulation. You can also purchase the package from us, and you can create your live replica of this. So if I pull out the notebooks real quick, you can see there are some things that are displayed here just for you to see. So this is what it would look like in real life, right? So the simulation is based off this, and what we are trying to do in this open class and the ones that are going further is to try and have you understand how best you can use this setup for educating yourself or a group of students you may be teaching, or if you're passionate about robotics, maybe you want more, right? You want 3 robots and you want a manipulator. You can also be able to learn quite a lot from having such a system, as it tries to mimic some of the real world use cases of robotics, right? So our simulation that we will be using will definitely be a clear, complete replica of the real world environment that you can create once you have acquired the box warehouse, right? So it comes with these 3, as I've said, and you get the panels as well, and you get the blocks that you can grip with the gripper that's in front of each of the 3 fastbots that we've got, right? So just to let you know where we are going with this. Okay, so I'm hoping you have all managed to have your simulation loaded. If you're still trying to, I will hang around a bit before we start hitting heavily on the theory that we want to speak about. So let me just check. Okay. All right. So as I've said, so we want to improve a bit, right? But at the same time, I also spoke about creating some type of a cliffhanger. So because we will be talking about executors and what they are, how they can improve our programs, how they can improve our nodes, right? There is what can be a lot at this moment for you to take in. So what you're going to do is we're going to show or demonstrate how you can create a multi-threaded executor, for example, right, which is basically a node that is two threads or two threads that are available for your node to have its separate callbacks run on those, right? However, there is a very clear way of doing it, and part of the way of making sure you allocate work correctly to these threads that you would have created when you're using something that is called a multi-threaded executor, for example, versus the default way of creating your nodes or running your nodes, which happens through a single threaded executor, is that you have to put your callbacks for your nodes into groups, right? So the main groups that we have got in ROS2 are mutually exclusive callback groups and re-entrant callback groups. So in this class, we are not going to show how this can be done. However, it is a prerequisite for a proper functional multi-threaded system. We're just going to show, right? We're just going to demonstrate how to create that multi-threaded node, right? But it is a strong need for you to have callback groups for you to be able to ensure proper multi-threading or proper allocation of work on those two threads, right? So by default, having declared multi-threaded executor, for example, in the ROS code that we see here in the node that we call obstacle avoid underscore multi, right? You will see that there is a creation of two threads, right? We create a multi-threaded executor here, and we select that we want two threads, right? This by default does not guarantee that your node will be able to allocate its callbacks onto those threads and run concurrently, right? If you do not use callback groups, right, to specify who goes where on the available given executors, your node will just default to using what is called the normal way of executing, which is basically doing things sequentially, right? So we've got re-entrant callback groups, and the other ones are mutually exclusive. So the default way of doing it is using a mutually exclusive system. So a mutually exclusive system just says, okay, if I've got 5 callbacks, I'm just going to run them one after the other, right? The order, you may not know which order will happen first. So this is just some of the general gist I wanted you to understand with regards to this, and why I was saying there's going to be a cliffhanger, because we're not going to show how to do this allocation of different callbacks to separate callback groups, right? Okay, so let me now go back to the top, right, so that we can start doing the way we can start doing our stuff the way we normally do. So I'm just going to list the things that we will be doing, so that you will be able to catch up with me on a step-by-step basis, right, when you look at the exercises that we'll be doing. So just give me 1 sec. All right. So as we do most of the time, right, we're gonna create a package in this open class. We're going to create a package that's called a improved obstacle package, right? Think about it as like an improved obstacle avoider, right? Because we want to put a little bit more things into that obstacle avoider we had created from the previous class, right? And then we're going to create two separate CPP scripts. One of them will show how to use a single threaded executor, or how to just declare a single threaded executor and use it, or assign your node to that single threaded executor, right? So what you have to know is, if you do not have this declaration made when you write your node, right? If you just write your node the way we used to do, ROS2 defaults to this kind of system, right? It will use a single threaded executor everywhere, no matter how many callbacks you've got, right? And then we're going to create another obstacle avoider script, but this time this is the one where we're going to create a multi-threaded executor, right? So we're going to create it and then see it running, but what I want you to understand is that what's happening behind that is still the default behavior, because we have not created callback groups yet. So we have to leave that for another class, so that we make an improvement on that to say, okay, this is what we call a callback group, and this is how you declare it, this is how you allocate your callbacks to that group, and you are guaranteed after that for sure, if I have two threads, then I have each one of them doing something that the other one is not doing, and it's happening concurrently, right? All right, and we're also going to get a bit more into detail about, okay, how do we create an RViz file to just visualize the LiDAR data, for example, because we want to see what our robot is saying, right? And so we're gonna go through just step by step how to create an RViz config file, and then be able to launch that when we launch each of our given executors, right? So that when the robot starts moving, when we launch that script that's going to make our robot start to move, we are going to also have the RViz window show us what the robot is seeing using the LiDAR sensor, right? So some of the things, right, the details, will, as always, subscribe to our fastboard _1 scan topic, and we'll also be publishing to the fastboard _1 command file, right? So these topics, right, they are the very same topics that you will use if we are going to be running our code on the real boardbox lab that we have got here, and that you can also acquire and configure to the same spec, right? And okay, so in addition to this, as always, we're going to also learn about what things we need to add to the CMake list file in order to make our scripts executable, right? In order to make them available in the ROS ecosystem, in order to make them available to launch them using ROS2 launch, or in order to run the executables using ROS2 run, right? It's part of the process of getting your package to compile properly and be able to be executed, right? Then we're going to launch this just to see the behavior, right? So in addition to the things I've been speaking about, the highlights and some of the things that can be difficult to understand with regards to the things we're going to be talking about, you can get some bit of notes here, right? I won't go through them one by one. However, I will keep referring to them as we go back and forth when we start explaining the code, right? So as always, let's create our package. So what I'm gonna do is gonna pull up the IDE, the terminal, and then we have the IDE on the other side, so that we can be seeing the things that I will be doing, right? So let me just check one thing real quick here. All right, no worries. All right, so what I'm gonna do is I'm going to navigate into the ROS2 workspace and the SRC directory. Then I'm going to list the things that we've got at the moment. So this will not be available in your ROS when you fork it, right? So what I'm going to do is I'm going to remove them so that we can start from scratch, right? So you can see how those packages come into be, how the RViz files come to be, right? So I'm just going to remove these here, these last three that you see here that I'm highlighting, and this one here, the fastboard description, that is there by default, so it's support package for the simulation, so don't worry about that. You should have it for some things to work actually for your simulation. So let's remove the folders first. So I'm just going to hit RMRF, and then we specify the folder we want to remove, and also specify the other one, right? Now if you list, you should be able to only have fastboard multi RVs and that one, so we're going to remove this as well. But since this one is not a folder, we're just going to not use RF anymore. Let's try that. Multi, right? Okay, cool. So now this is what you should be having, right? So if I clear our terminal, you can now see the things that we should have in that folder, right? So what I'm going to do is now I will be using the instructions that are given in the notebook, right? So we go step by step, and you can also see how you can leverage this notebook to learn things, or to try and remember the things that I did, and the order in which I have done them, right? So you can configure your window the way you want, right? So normally I myself, I want to be able to see the terminal and to see the IDE on the other side, and to have the notebook on this end, right? For you can use this button that we've got here to create a custom layout. So if you have dragged windows in certain ways, you can just click save custom layout, or you can use the already predefined ones. For example, if we want to see it like this, you could just click that, right? And you could do that. So just to make your life easier, for me, I'm just going to return to my layout, right? And then we'll go step by step. So let's hide this real quick. All right, so you can be copying and pasting the code that's given, but some of the things will be typing letter by letter, right? So what we're going to do is, in the SRC folder, we are going to create a directory that's called improved obstacle package, right? Underscore package, and then you will have something like this to show that your folder or your package has been created, right? So I am going to just run through what we are doing here, right, so that we at least understand. So let me maximize this so we can have a bit more info. So if you press a up arrow, right, once you've copied and pasted that and press enter, you can return to the previous command that you executed, right? So what we're doing here is we are typing ROS2 package create and improved obstacle package, right? So this is the name of the package. It can be anything else that you want your package to be called, right? And then what we're doing here is we are specifying the build type. So as you know, maybe if you don't know, it's good information to know, most of the packages that we create for ROS2, they are either Python packages or C++ packages, right? So when you specify the build type, right, is amend CMake, your package is a C++ package, right? If you have got the build type specified to amend Python, for example, your package is going to be a Python package, right? There are also other ROS clients like Rust and Java. They have their own build type or their own flag representative to say that you're creating a ROS package of that type, right? And then what we are doing here with the second flag that says dependencies is you are specifying that, okay, I am creating my package that's called improved obstacle package, and I want it to include these other libraries, right? So I want it to be in C++ terms to be linked with these other libraries, because they are going to aid in the way in its functionality, right? So you're going to see why we have to say why we need RC or CPP, why we need geometry MSGS library, why we need the sensor messages library, right? Okay, so with that having done, let's go back to our notebook and we can go real quick to the next step. So what you're going to do is we're going to start by creating a single threaded obstacle avoider script, right? So you can copy here, right, or you can just tap there and Control A in your notebook to just highlight, then Control C, so that you have the contents of that copied. However, we have not created a script that is called obstacle avoider underscore single.cpp yet. So how you should do it, if you don't use the IDE, is you can navigate to that directory, package directory that you've created that's called obstacle avoider package, right? So here we have got it called improved, sorry, okay, improved, just right. So cd, you type I and then you press tab, it auto completes for you. And then if you list the contents of this, you will see that you have got other things that have been added to your package by default. So you've got CMake list, you've got the include directory, you've got a package XML, you've got SRC, right? So the CMake lists, we'll speak about it a bit more when we modify it, and the package XML as well. The include directory is there for you to put header files. If you're going to be using a header files when you develop your nodes, or for anything else that you develop in ROS2, either you're creating a package that's going to be used as a library rather than one that is executed, then you find yourself wanting to create header files. So your include directory is there for that. So it's created when you create the package by default. Right? The SRC folder the same way. However, the SRC folder is the one where we actually create our nodes. So what you're going to do is we're going to navigate into that directory, and in that directory we're going to use the touch command to create the script that we want. So if you type in touch, then you specify the name of the script that you want to create. So for us, it's going to be obstacle avoider single.cpp. So I'm just going to copy this real quick so that we don't waste time typing it out. So you press Ctrl V, then enter, and now if you list what is in the SRC folder, you see that now we have got an obstacle avoider single.cpp. So you can then copy the contents of the second cell, right, and add that to your script in the IDE, right? So if I open improved obstacle avoider, so let's drag this one more bit to the side so we can see the names, then we can have our code pasted there. So let's talk about this a bit, right? So I will maximize this really quickly, right? So what we have got here, so the normal way of declaring a class, right, in C++, this is how we do it. However, for us though, the important thing to note is that remember that we wanted RC or CPP as a dependency, right? Because you can see one of the reasons is that we are inheriting from the node class, from that namespace, or from that library that we have included. So that is very important. And then here we specify the name of our node that you're trying to create, right? And it has got an argument, right? It takes an argument that determines is there an obstacle in front. So the precondition is always initialized to false, right? And then here what we're doing is we are declaring a subscriber. So remember that for your node to work in such a way that it allows or it exhibits some type of obstacle avoidance behavior, there has to be some form of perception going on, right? So the perception that's happening with regards to our obstacle avoider in this case is happening via a LiDAR scan data. So it receives LiDAR scan data via this subscription, right? And in that way, we constantly have information about what is the thing that is in front of the robot, to the side, to the left, to the right, to the back, right? And that's why we need to subscribe to that, so that we get this information coming through, right? And then what we are doing here is we are binding, right? So we are saying that every time you receive this LiDAR scan data, execute this particular member function of the class obstacle avoider single here, right? That is what is happening here. So you are when you do this, you are saying an instance of this obstacle avoider single a class must execute this particular member function, right? That is very specific to this instance, right? That's what's going on here. Otherwise, if you have not done this, then you're saying, okay, maybe any other instance of that can execute that, right? So it's very important to have this, because you're saying bind it to this specific instance, so that there's no confusion in case that you have multiple obstacle avoider single objects that have been created, or that are in the same memory, for example, or that are running on the same machine, right? And then what we're doing here is we're also creating a publisher, right? Because remember, what we want our robot to do is we want it to be able to perceive things either that are in front of it, to the left, to the right, and then when it sees those things, we want it to be able to react to them in such a way that it does not collide, right? That's why we have this, right? So we're also going to see, right, a slight difference from the previous class, that what we have done with this one is we have tried to separate, right, the member function. This is, we call it a member function in C++. In ROS 2, it's called a callback, right? So it's the thing that it's the function that is executed upon receiving some particular message, if it's a subscriber, right? In this case, we can call it a member function because it's responsible for publishing, but you get the flow, right? So in this regard, we are saying when your subscriber is received information and is perceived the environment via LiDAR, we want it to be able to tell the publisher for the command velocities what to do with regards to that information, right? And here we have a timer, and the timer is responsible for clocking the execution of the publishing of the commands for velocity, right? So if you go here, so you've got the timer callback is the function that we're binding to the timer, right? So what we can do is we can go down and look at what the timer callback is doing, right? If you see what the timer callback is doing here, it is responsible for setting the linear and angular velocity and also publishing them, right? You can see that the last step in line 71 here is we have got the set command velocity values being published, right? So they are published at a particular frequency that is determined by the specifications of our timer, right? In this case, every 100 milliseconds, our timer fires, right? So this corresponds to like 10 hertz. So you're publishing like 10 CMD val messages per second, right? So depending on how fast your robot is going, you may need to increase or decrease this. So it's very important for you to understand the significance of the rate at which your timer runs, right? Okay, so let's go to okay, so here this is just a logger. However, with each of the things that are being specified or that are being created in this constructor, right, there is a corresponding function to each one of them. You can see that this is the scan callback, or this is the definition of the scan callback, and you can see the scan callback is being bound to the subscriber, right? The same applies here. We're not binding it to anything, but we're just declaring it because you need to have an object of type publisher to be able to then call publish on it, right? Okay, so that is that. So let's go in a bit more detail, right, about the things that correspond to why we are going to be speaking about multi-threaded executors, and in comparison to single-threaded executors, right? So here you can see there is no place that we specify what kind of executor is going to be doing the job, right? What this means is that you will have all these things, right? This timer callback, right, will be running on the same thread that your scan callback will be running on, right? So think about it as like one pipeline. So one thread is like one person doing the job, right? So they have got two tasks, right? In this case, the two major tasks is this one person has to receive LiDAR scan messages. At the same time, this one person has to be sending command velocities with specific attention to the kind of data that they've received from the scan callback, right? So this is one person juggling these two tasks, right? But computers are really fast things, right? So if you think about the fact that the timer callback fires 10 times per second, right? And this is processing at the rate at which the LiDAR scan data is coming, right? So if you have got like your scan messages coming at let's just say a frequency of 50 Hz, for example, right? Because this callback that we call scan callback is bound to your subscriber, right? What it means is that every time a new message comes, this scan callback has to fire, right? It has to process it, right? You have got other mechanisms in ROS 2 to deal with excessive data and to deal with overflows, right? So what happens when a lot of data comes to the CPU and it cannot process it, right? You have got other things that are set in place for that. However, what I want you to understand from this is that it has to execute at the frequency at which the data is coming, right? So it may be coming at a speed that is faster than 10 Hz, right? But remember, the data is coming at 50 Hz and the publisher has to be publishing at 10 Hz, right? So that means your thread must be running at some way higher frequency than that per second, right? So this is where you can begin to see why it is important to have a more than one thread at some point, right? In other applications, right? It's basically because of this, right? You have things that are coming in or things that are due to happen at a certain frequency, and for one thread, given the type of hardware that we've got, it becomes very difficult for you to be able to have a single thread be able to do these things exactly at the time at which it is expected to do. So this is where a multi-threaded executors become important, right? So let's go back to our notebook and try create another script, right, that demonstrates part of the way of getting to using multi-threaded executors, right? I say part because remember what I said earlier, that there is half of the process of doing that's missing, which is basically creation of callback groups, having callbacks allocated to those callback groups, right? But we have to start somewhere. Okay, so let's go here real quick. So now this is our multi-threaded this is where we are creating our multi-threaded executors, right? So we're going to do the same thing and then we're going to explain the code step by step. Okay, so let's create another script here. So as always, touch, and then you specify the name of the script that you want to create. So let's copy this real quick and we can edit here. All right, so now you can then copy, you can use this, but sometimes if you're working with Python, for example, it can introduce foreign characters, so I prefer that you just tap that cell, Control A, Control C, and then you have copied the code that's given in the notebook correctly. So, and then you just open the script in the IDE and then you save the file, right? Now, okay, let's do the same thing. Let's open one more time. So we have spoken about the things that are happening. Most of them have not changed, right? So you still have your constructor initializing a subscriber that subscribes to fastboot1/scan, and you still have a publisher that is also publishing to the same topic, right? Fastboot1 command vel, and then you still have a timer, right? And now what I want us to do is, the rest of the stuff is the same, right? But what I want us to do is, let's look what's happening here first, right? So what we have to do is, we are declaring a multi-threaded executor. So remember, we did not declare an executor in the previous script, right? This one does not make any declaration of an executor. However, you could explicitly tell ROS that, okay, I want a single-threaded executor, right? That's, maybe you want to be very specific about it, but you must understand that by default, you not having done that is just going to resort to that, right? But in this case, we have to specify that we want a multi-threaded executor, right? For the case that you want a single-threaded executor, you can just replace multi and then a single-threaded executor. Then you give that executor a name, right? You call it executor and give it options to initialize it, right? And then after that, you add your node to that executor, right? So the node here is the obstacle avoider node, right? So this class here, this node that we have created at the top here, is the one that we are now giving to our executor, and our executor now will be responsible for, if we had done the proper callback group allocation, declaration and allocation of callbacks to those groups, right? What would happen is that your executor will be the one that's responsible for now telling each one of those callbacks within that node to say, okay, you're going to execute on this string and you're going to execute on this string or on this thread, right? It's all the job of the executor, right? However, it is important, for the sake of us to start, it is important for us to know how to do that. So that's why there is this, right? So remember, the number of threads that you can declare, right? Or the number of threads that you can give to your executor. In this case, we're giving it 2 because we are under the impression that when we are going to do our next open class, we're going to try and assign the different callbacks that we've got in our multi-obstacle avoider here to those 2 threads, right? So the callbacks that we've got here is, we have a timer callback, right? That is responsible for publishing velocities at a particular frequency, right? And the frequency for this is 10 Hz, if you remember, as we said earlier, right? Because we have a space of 10 milliseconds between each firing, right? And then we have a second callback that we call scan callback, and this scan callback is the one that's responsible for receiving and processing LiDAR data as it comes in, and then doing something about it, or doing some form of processing of that LiDAR data before a decision is made about whether your robot is going to go forward, backwards, rotate left, rotate right, right? Okay, so now the thing that is of greatest importance is that once you start dealing with more than one thread, right, and you have shared variables. When you say shared variables, they are things that are common between the scan callback and the timer callback, for example, right? And those things, right, let's look for an example here, if I can find one real quick. Okay, let me look. Right, you've got a data mutex here. Let me check. I'm trying to find an explicit example so that it doesn't go around our concepts here, but okay, let me explain in theoretical terms for you to get the idea of why I'm saying there might be shared things, right? So if you look at the way we are declaring our scan publisher, right, it's declared as a shared pointer, for example, you say that, and then our timer is declared as a shared pointer. The same thing applies to the data that comes in from your ranges data, right? It comes in, it sits somewhere in memory, right? And when it sits there in memory, just hang on one sec. All right, let me okay, so I was saying you have LiDAR scan data or your ranges data come in, and then you have it sit somewhere in memory. However, when it's being handled by more than one callback, right? This is the sharing of resources that I'm talking about, right? So each time you have got data that's shared between two callbacks, and you assign those callbacks to different callback groups, right, or to different threads, right, you run into what are called rest conditions. So this is the case where you have two callbacks trying to access that shared resource at the same time, right? So it becomes very important for you to be aware of these things as you start being dealing with a multi-threaded executors and having callbacks that share data, right? In our given setting at the moment, there is the sharing is not very much explicit, because what's happening is that we have a scan callback that's publishing, right, some that's receiving data, and then we have a timer callback that's responsible for publishing command velocities. However, within the scan callback, right, this is the important thing, we are still solely relying on what the scan callback gives us, right, to be able to set the mean distance, right? So if you look at it in this case, right, mean distance is our almost shared thing here, because you also need to know what the minimum distance is before you set the direction in which your robot is going to turn. The other thing is you also have got this obstacle ahead boolean value, right, that is responsible for telling, or that is set to true or false depending on whether there's something in front of the robot. So that is the part of the ranges data that is specific to the front of your robot, right? So these, right, when we say shared variables in general with regards to a class or a node class that we've got, right, they are mostly characterized by being declared as class member variables, right? So they are not declared in the functions themselves. What I'm saying is they are not declared in the callback itself, right? They are declared outside the callback and they are used within it, right? Or if you look at this case, right, so they are declared outside, which means they're class member variables, but they are being used in our scan callback, for example, right? It's being set and unset based on what based on the processing that's happening at the beginning of the callback itself, right? So it's shared because it's in the class global namespace, if I could say that, right? Because it is outside the scope of each callback, but it has to be set, or it has to have its values changed by one or more than one callback, right? This is where we get into the area of, okay, do we need to actually synchronize the processing of this information? Do we need to set some type of a mutex to govern who accesses that data first, right? So these are the complications of a multi-threaded executors in general. So what I'm going to do is I'll get back to this slowly as it comes, right, as we try to see some of the demonstrations. What you're going to see is that us running a multi-threaded obstacle avoider and running a single-threaded obstacle avoider, there's probably going to be no difference. Why? Because if you remember what I've said, by default, if you do not allocate those callbacks to a separate callback group, ROS2 just defaults to executing them synchronously, which means that you're going to have what you have declared to be a multi-threaded executor, or our obstacle avoider multi here, to be multi-threaded, not actually multi-threaded, because you have not done the callback group declaration and then allocating of callbacks, right, which is a topic for another discussion. Okay, so now let's finish up our exercise here. So what you're going to do is we want to also be able to visualize the data, right? So to visualize this data, we are going to create an RViz config file, right? So here you've got the specification of what the RViz config file will look like. So remember, you cannot you will probably be able to do this step like line by line, but this is tedious. This is a generated script, right? That happens after you do something. So or after you create an RViz file, right? So what I'm gonna do is I'm going to open RViz real quick and then create add these things to our RViz file. So we have got our simulation running. So what I'm gonna do is, if you open graphical tools, and okay, let's do it this way first. So if you go here and in your terminal, let's just clear so that we start from scratch. So in our terminal, we are going to go to our package directory, right? In here, this is where you've got include package etc, right? So within this improved obstacle package, we want to create another folder that's called config. Let me just double check. Config RViz, for the sake of keeping the RViz configuration that we're gonna use, right? So let me check. Yes, we're gonna create a folder that's called RViz config. Okay, right. Okay, so it's gonna be called config. So I will open the terminal one more time, and then let's make directory here. So you could name this folder any way that you want. Other people might call it like RViz underscore config, but for our purposes here, we're just going to call it config. Then you press enter, and then within that folder, right, so you type cd config, and then you list. You see that there's nothing. So what we want to do is we want to create an RViz configuration file that's called obstacle avoidance.rviz, right? And then we want to configure that RViz file. So what you're going to do is we are going to touch. You can do it this way, or another way of doing it is you type in RViz. I think it won't allow me to do this, so let me just do this manually. So let's first create it, right, and then create it empty. So obstacle avoidance .rviz here, and then you press enter, right? Now you have your config file, and then we then do RViz2 D, and you specify the name of the RViz file that you want to open. So what this will do is this will launch RViz, but it will be an empty RViz. So for you to eventually end up having the things that are similar to this, or the configurations that are similar to this, you would have to modify the RViz window, or the configurations of the RViz that's going to load, right? So if you open here, and you can say file, or let's do something like this. I think this will be easier. So let's add something to it, right? So when you're here, you can add multiple things to your RViz config file. So the first thing that we're gonna do is we want to be able to add let me check why this is going this way. I think it's not launching the way I want to, but okay, never mind. Let's do it the other way around. So because we have declared our RViz file very much empty without anything in it, let's remove that, and then we can do it the other way around. So if we say let's clear, and then let's remove the current file, right? And then we're just going to launch RViz by default. We're not going to give it a name. We just want it to launch with the default configuration, right? Just RViz2, and then you press enter. So what this will do is it will launch RViz in its default form, right? It's not forced to look at a configuration file like what I had done earlier. And then you have it like this, right? So this is more like the way it will look when you load it from something else, or if you load it from a particular ROS object, right, that you know. So what we're going to do is we're going to add things that will allow us to visualize what our robot is saying. Remember that our simulation is running, so let me just pull that up real quick. So our simulation here, you can see that it's running, so that means we've got RViz data being published, right? So if I go here on in the terminal and you say ROS2 topic list, or let's just say ROS2 topic echo, and we want to echo fastbot 1 / scan. Okay, fastbot 1, right, and you press enter. You see that there is already data that's coming. This is because the simulation is running, right? So if you were connected to the actual robot itself, you will get data still being published. For example, when you have your robot connected properly and the topics are being published correctly, right? So this is a good thing, right? This stuff that we're seeing in the terminal is the stuff that we want to be able to visualize in RViz, right? Using or maybe when we run our robot, we want that type of stuff to be happening. We want to be able to see where the robot is going and how the LiDAR scan data is changing, right? So as I've said, it's a good thing. So let's go back to our RViz file. So we've got configuration window, graphical tools. I'm hoping it's still open. Why is it not showing now? Did I terminate? Oh yeah, I did. Okay, so give me 1 sec. Let's check here. So we're going to launch RViz one more time, just like this, in its default form, right? So type in RViz 2, press enter. You don't add anything else in front or any flag, and then you have this. So let's maximize this. So the first thing we want to add is we want to add the LiDAR scan data, right? We want to be able to see that, so we have to add a display. So we want to add a laser scan display. So if you go here and you look for laser scan, right, if you look by display type, you'll find that there is this tab. Okay, hang on 1 sec. I think something is glitching really quickly here. By display tab, let me close it and open it one more time. Okay, good. Alright, so we want laser scan data here. If you double tap it, then you have it added. But okay. Okay, so laser scan data. Where is it now? I think I have got a bit of a drag here. Okay, this one here. So if you double tap it, you should have it added in the left column, right? So we don't want pause array for now, so let's remove this. If you go and remove, then you should be able to go. And then now we have got laser scan, right? And here what we want to do is, if you look, you can actually see the things that are missing, right? Error subscribing. So there is some issue with the topic to which you're subscribing, or you have not configured that yet. So if you go here where it says topic and you tap on that arrow, then you should be able to specify which topic you're subscribing to. So let's first check here. So yes, subscribing topic name empty, right? Which basically means you have not subscribed to the topic yet. So let's look for a subscription real quick. So configuration topic, and yeah, and you double tap next to topic, you should be able to see a drop down window, so you can subscribe to Fastboard 1, Fastboard 2, or Fastboard 3, right? But for us, because we're working with Fastboard 1, we want our latest scan topic to be subscribing to that, right? So that's how you add visualization, right? So the other thing you also want to specify is your fixed frame. So our fixed frame in this regard, we want to make it odom for the Fastboard. So let's check here really quickly. By default, it's going to launch with the map frame as the default. So let's see if we can change this really quickly. So what I'm doing here is you can be able to do it. I'm showing so that you can be able to do it. Otherwise, I could have just copied and pasted the stuff that we've got in that. But let's finish this fixed frame thing first, and then we can resort to how it would look like if you have done everything else, right? So I want us to be able to correct the fixed frame here, so we can add. So our fixed frame, we're going to specify that we want our fixed frame to be Fastboard odom. Let's see if it will show up. Now you see you've got a bit of squares that show what the robot is seeing, right? So if you go here and you change the size, right? So let's say we want our flat squares to be slightly bigger, so let's make them 0.25. You should be able to see. Okay, so this, based on where our robot is looking, this is what it will basically what it is basically seeing, right? Given the setup of the robot and where it is facing and how the LiDAR scan data sits on top of the robot, right? So what I'm going to do is I'm going to try and move the robot a bit, and we want to see how this changes, right, when we move the robot. So if you double tap, if you don't want to use teleop and you just double tap on the robot, you should be able to move it with arrows, right? And you can see that this is what your robot is seeing. So right now, if we zoom in one more, just give me one sec. If we zoom in so that we go closer and closer, we can see that our robot is within these three walls here, right? So if we tap on it again and we rotate our robot, so you can use arrows once you've tapped, right? Once you've tapped your robot, you can use arrows to control it in the simulation. So if we have a robot rotate, now it's seeing, you can see here, if we zoom so let's have this set up correctly, and if we zoom in RViz here, you can see you've got these things that are representative of the other robots that are on the left side of the robot, right? So let's move it towards that to just see how those things will change. Right, so I want us to go, okay, and okay, so you can move it and you can see now, okay, collision. But basically this is how you can visualize what the robot is seeing, right? So if you move it towards that corner, you can also see, if you rotate it in the direction, you can see how that data is changing, right? So this is just a visualization of the data, right? There's nothing else, there's no map that's shown, there's nothing else to really show you where the robot is, except you have to rely on the red squares that are showing you, okay, my robot has got something in front of it and it looks like it's straight, it looks like a wall, right? So this is what it is seeing with this particular sensor, right? So what I'm gonna do is, let's save this config file, right, so that I can be able to show you this is what it would look like when you have added all the other stuff that are shown here in the notebook here. So to save that, or to save our settings, right, and generate something like this, we have to go on, you have to return to your RViz, and then let's maximize it to make it easier to visualize. If you go on file and then you specify save config as, right, so your config now has got the fixed frame set to the robot odom, and then the LiDAR scan, the laser scan set to Fastboard /scan, right? So these are the configurations that you're saving, right? And if you type in save config, right, this is where that folder that we created as config becomes very important, because by default it will be saved to this hidden folder that's called RViz2, right? So what you want to do is you want to navigate to the directory in which you want it to be saved, right? That will be easier for you to return to eventually, or do some work, right? So in this case, if you open user and then you have your ROS2 workspace, within that workspace is where we had our SRC folder and we have our improved package there, and we created oh, hang on one sec. Within that, we have created a folder that we called config, right? So we want to save it in config, right? Because that's what we agreed on earlier, right? And we also want to specify the name, right? So the name itself, as I've said, we're going to be using the name that I've given, which is this one here, obstacle avoider .rviz, right? So if you just copy this and you paste it in that window, then you will have your version of this saved in that directory, right? And you can make even more modifications, and again, this time you wouldn't click save as, you just click save, and then it will be saved to that, right? And then let's see if we can paste it there. I hope it allows me to do that. Okay, issues. Alright, no worries. Let's just type obstacle avoider.bash. Obstacle avoider.rviz. Avoidance. If you just press enter, then you have the .rviz edit for you. So okay, let's just press enter, and now we have saved our config file, right? So if we navigate to the directory in the terminal explicitly, we should be able to see that file appear there. And if you want to open it in the IDE, we should be able to do that and be able to see what it looks like. So we're just going to type in a ROS2 and SRC, enter, and then we want improved obstacle avoider, right? Okay, there we go. And config. Okay, let's see if it shows up. I hope it does. Right. And then you list the contents of that directory. You should be able to see that you've got obstacle avoidance.rviz. So remember earlier we were launching it without using any config file, but now we have a config file available. So we're going to launch it by specifying the stroke D and specifying the file name, right? So this is how you create an RViz config file that's specific to what you want to run. So what you're going to do is I have had this done so that you know how to do it, but for the sake of progress and for the sake of the other stuff that we want to be able to visualize, I'm going to copy this really quickly so that this becomes my default config. So I will modify the one that I've created by adding things, and then we'll just finalize by adding the launch files that allows us to visualize when the multi and the single executor files are running, or when the single threaded executor ROS2 nodes are being run, right? Because that's what we want. We want to be able to launch the node and also visualize what the robot is doing in RViz, right? So I'm going to copy this real quick into the obstacle avoidance RViz config file that I had created. So what it will do is it will override everything here, but it will override it with custom values, right? So I've saved it, and then when we will launch, you will see that it will launch in a different way, but that's configurations basically. Okay, so let's go back to now finishing and adding the other stuff. So we want to launch our obstacle avoider single.launch.py, and we want to be able to launch the multi one. And so we're just going to create the launch files at the same time. So let's do that really quickly. So if we go here and you navigate one folder down, and you list. So you should be able to see that within this we don't have a launch directory yet, and our notebook specifies that we must add these things to a launch directory. So a launch directory for a particular package is always contained within that package itself, right? So we want to create a launch directory for the executables that are within this package. So what we will do is we will make a directory here, right, and then call it launch. So by default, or by let me say by convention, this is how we name the folders of a launch file, right? And then we're going to open that, and again use the touch command to create our launch files. So we're gonna do touch avoid a single dot launch, 1 sec. So avoid I think I'm having very slow response here, so avoid a single dot launch dot py. Okay, not good. Dot launch dot py, and then we press enter, and then we're going to create another one, this one here. So I think to prevent typing and verifying, let me copy this and then paste. So we'll use the touch command one more time. So touch, and we'll paste here avoid about.launch.py, right? So oops, Control C, I added an extra symbol there, so it was trying to execute something. Okay, now we've got our launch file script. So as always, we're gonna copy this and edit via the IDE, and here now we have our launch file, and this is the single one. So let's add this really quickly. I'll go through each one of them after we've added all of them. So let's do this. Okay, cool. Let me minimize this really quickly to avoid confusion. Okay, and then now let's go to the multi obstacle avoider so that we can also add that to our package. Right, this one here. So Control A, Control C, and then you can add that to your launch file. So that one I've got here, then we paste. Now, okay, so to just run through what's going on here, since we are almost out of time. So what we're doing is we are launching two nodes, right? So the two nodes that we're launching is, one of them is an RViz node. So that node is the one that will be responsible for launching our RViz window, right, or running RViz for us so that we can visualize what our robot is doing. And then the other one is responsible for running our node, right? In this case, our node is the avoider multi. So that's the version of the obstacle avoider that is using multi-threaded executors, right? The incomplete one. Remember, I told you it's very important to know that because we have not done that yet. And then again, we have the same thing with the obstacle avoider to launch the single. This was the single version. The multi version has also got the same thing. You still are launching RViz, right? This is the executable, and the package is called RViz2. So everything in ROS is a package, right? It doesn't matter you're dealing with something that is external, it is still a package. So you see, even the way we launch RViz here is we launch it like a normal node, but we have not developed RViz to the package ourselves. We're just using it, right? And we also have the same thing happening here. The output to the screen means that when you run your node, you're getting something in the console, right? And also having windows being displayed. And then here what's happening is we're specifying where to get the executables, right? For example, improved package here, it will be found in the shared directory. So if you go in the build in the install folder, you see there will be a shared directory for each package that you compile, right? This one. So this is where your executables will be found. And then here we are specifying the path of the RViz config file, because when we launch RViz, we want it to launch with a particular config file so that we can be able to ensure that we're launching the RViz that will display correctly the way we want it to display. Okay, so now having that said, so let's do some modifications to our CMake list file so that we can make those executables available, right? So the CMake list file, because our multi-threaded and our single-threaded nodes are within the same package, the modifications that we'll do will be to a common CMake list file, right? But I will explain a bit more where each executable is linked to its particular dependencies and being installed, and the launch files, how they're being installed, right? So, but for now, let's paste it into our CMake list file, and then we can be able to see what's going on. So let's collapse this and this one too. So let's open, we want the CMake list for the package that we're working with, which is the improved obstacle package, right? And then here we open it, and what you have to do is you have to copy and paste this here. So I will explain what each one of them is doing. So let's start from the bottom. If you'd allow me to maximize this real quick. So what we have got here is, because your launch file is to be an executable, I'm putting quotes because it is an executable, right? Everything that you do is some other executable running somewhere else on the machine, on your computer, right? So because your launch file is a type of an executable you have to install, right? Because your RViz config files, they have to be found at runtime somewhere, they have to also be installed. That's what we're doing here, and they are being installed in the shared directory for our project, right? So remember when I showed you that in the install folder there is a shared directory within the package directory here, this one, it's put there because by default this is how ROS packages work. They go there to look for things. So the same way, you must also make sure that they're installed there, otherwise you have to make custom modifications if you have them saved elsewhere, right? So that's what is being done here. And here we are also installing our executables, right? Our executables are being installed in the lib directory, right? So by default, when you type in ROS2 run, ROS2 launch, or ROS2 run specifically, not launch, ROS2 run, right? It has to look for an executable that you want to run, right? So there are two ways you can run if ROS2 executables. You can run them via launch files when you want to run multiple, or you can run them directly by calling ROS2 run. So when you call ROS2 run, you are looking for an executable, but the system has to look for that executable somewhere in an agreed workspace, in an agreed folder, and that folder is the lib directory here. So we have to install our executables there, and we give them names, right? But how do we create executables? In C++, as you know, executables are created when you compile, and then you do the whole pre-processing, compile, linking, and everything, right? So the process of creating executables is what's happening here. So here we are saying create an executable from the source file that's called obstacle avoider single, right, .cpp, right? This is our source file, and we give it this name, right? That's why you see when you specify the executable, we don't specify what the file looks like or what the script is labeled as. We specify the name that we would have selected in the add executable, right? And then what we're doing here is we are linking those dependencies. If you remember from the earlier time that we said, every time you put stroke dependencies and then you specify that you want RC or CPP, geometry messages, sensor messages, right? They are the libraries that will be linked when your executable is being put together so that it becomes one executable binary at the end of the day, right? So this is where the linking phase is happening, right? For this particular executable, right? And that's the responsibility of target dependencies. You are telling the ROS compiler or the compiler that's used by ROS to say, when you build these executables, link it with these libraries, because it is using a functions, information from those libraries, right? The same applies to our obstacle avoider multi here. It's the same thing, creating an executable, then linking it with its dependencies so that it becomes executable, right? All right, and remember you have to add all that stuff before the amend underscore package, otherwise you get an error, right? So let's compile this and try run it. Run each one of them to see if our robot will exhibit the behavior that we want for now at least, right? So you can just copy this, and this will allow you to navigate to your ROS2 workspace root directory, which is the ROS2 workspace for us by default. It can be anything else underscore workspace for you, but it's important to compile in that workspace, otherwise you have a lot of overlay issues when ROS is trying to look for the things to execute, right? So always compile in the ROS workspace. Alright, so now that we're sourced and compiled, let's launch the single avoider and see if it does some things, right? You never know, it may do things that we don't expect, and we want to know why eventually, right? So it's being able to figure out that, okay, there's something in front of me, let me modify my path, right? So it's good stuff, right? So let's stop this one sec and try the different one. So we're gonna try with the obstacle avoider, right? And the other thing, by the way, it's very important to understand why is it that it keeps going when we have pressed Control C. So the issue is, I think we spoke about it in the previous classes, you can also make reference when you watch them later, but the message that was last published is latched, right? So unless you create a custom workaround which triggers a default setting to velocities of 0 on both angular and linear, when you press Ctrl C, the subscriber or the command for subscriber in the robot or in the simulation itself, even on the real robot actually, if you don't implement that, will hold on to the previous values that have been published. That's why you see it keeps on moving. So you have to publish command for values of 0, right? Before or in some form of way, right? Either within your script or you have to do it explicitly within the terminal itself to make sure you zero it out. So there was a command that I put somewhere. Oh, I can't find it. To just zero out those. Let me just check if I can't find it. It's available in the previous classes that we've done. So let me show you that it's still moving, just to be sure. So if you can see it's still moving, right? It's because it is latched onto those values. So it's important, if you design your robot eventually, or if you're using the actual BotBox warehouse robots, you have to implement some form of default setting, so that when you press Ctrl C, your node will reset the published velocities to 0, and your nodes will, or your subscriber that subscribes to command velocity, will latch to those values and ensure that your robot stops, right? Okay, so let me check, do I still have that command? All right. I don't think I have it in this notebook, but no worries. We have gone through a lot of stuff in this open class, but I hope it gave you a grasp of the general concepts that we were trying to illustrate, and also created some curiosity, right? So that you can be able to go into this course, for example, the ROS2 Basics in 5 days, to be able to try and understand in more detail, like what does it mean to have these things that we call executors, right? Or what does it mean to have callback groups, or to even go to an intermediate version of the course to try and understand in more detail these things. However, we'll leave them out for another class. And I do realize that something did not launch, but give me one sec. Something did not launch as per our expectation here. We didn't get the RViz window, but anyway, that's enough for this class. We have gone beyond the allocated time, but no worries. You've got the notebook, and you've got us and our courses to go back to. And by the way, remember, you can do all that you did in simulation, you can also do it in the BotBox way. So yep, I wish you all the best, and until next time, bye bye.